Okay. Testing, testing. Okay, I guess we can start. So last week we talked about some advanced models, some modern versions of convolutional neural networks, right? So today, as usual, we're going to start with a brief recap of what we have learned in the last lecture. Okay. So what we have in the last lecture is that we start with the first modern convolutional neural network, which is AlexNet. And you can see that compared to the decades-old convolutional neural network, which is LearnNet, it has more layers. And what makes it different is that they're using ReLU activation as opposed to sigmoid activation, and it has more layers and it has dropout. So all this is to make it more efficient in terms of modeling larger images with larger data set. Right? The model is larger, therefore you can capture more complex pattern from a larger data set. And we also briefly talk about the concept of receptive field, right? And this concept of receptive field, it will appear again today. So if you look at your first layer, receptive field, if you pick one pixel in your first layer, the receptive field is 3 by 3, right? But if you have multiple layers, if you stack multiple layers of convolutional neural network, that will give you a larger receptive field. For example, here, let me bring out the laser. So if you're here, then your receptive field in each pixel is actually it's no more 3 by 3. It's now 5 by 5. Right? So you get a larger receptive field by having more layers. Okay, and then we also talk about different versions of modern CNNs, right? And the one that comes after AlexNet is VGGNet. So VGGNet, it kind of replaced a very large kernel in the first few layers with smaller kernels, but with more layers. And they are the first to use this notion of block. That means a block can consist of multiple layers, and you can repeat the block again and again to stack a very deep neural network. So this is VGGNet. And after VGGNet, we talk about NIN, so network in network blocks. And the intuition of network in network block is to introduce more nonlinearity. So basically, it's going to replace one convolutional layer with one NIN block. And in each NIN block, you're going to have one convolution layer followed by two 1-by-1 convolution. And I hope you still remember what 1-by-1 convolution is. So just take all the pixels from the same position and perform some kind of fully connected layers, right? Equivalent to this kind of operation. And the next network we talked about is fast forwarding to GoogleNet or InceptionNet. And that's the first idea that uses parallel concatenation. Basically, you have multiple paths, right? You have 4 paths here, and then at the end, you concatenate all your results. This is GoogleNet. And then you have what? We also talk about what they call internal covariance shift, right? Internal covariance shift. Normalization. To cope with this, we use some form of normalization. We start with batch normalization, right? And then we kind of say that the batch normalization, you normalize across different data point, different position in the same batch. You can actually normalize from a different perspective. So you have layer norm, and instance norm, and group norm. Okay. And fast forwarding to another neural network, which is ResNet. The key idea of ResNet is to add some residual connection. It's called residual connection or skip connection. So basically, it's just instead of going from the lower layer to higher layer by stacking a lot of operations, we basically have some residual connection or skip connection between them, such that you can. So this is the basic idea. Right? So in each layer, instead of f of x, you're gonna change it to x plus f of x. So this is to make sure that your function class is actually nested. Okay. And then we talk about dense net. Right? Dense net is basically replacing the addition operation in residual net with a concatenation. So this is much more complex, but it achieves better result. Okay, so this is dense net, and at the end of the last lecture, we talked about transpose convolution. Right? So what's transpose convolution? You can think of it as the inverse version of convolutional layer. In convolutional layers, you have one input feature map, and you apply some kind of convolutional operation to kind of process the information, right? And when you process the information, usually you're gonna get a resulting feature map with a smaller spatial size, right? There is a picture here, right? As you go forward, you're gonna have a smaller spatial size, but sometimes it's actually desirable that you would like to reconstruct the image, kind of modify the image a bit and then reconstruct the image. So this calls for the inverse operation of convolutional layers. Also, this is what we talked about, the transpose convolution. And this is the naive version of the transpose convolution. So this is input, this is output. You can see that feature map size gets larger. And we also talk about how to emulate transpose convolution using regular convolution. So this is the emulated version. Okay. So this is a very brief recap of what we have learned in the last lecture. Okay, so before I move on to the new content today, want to make sure no questions from you, or any questions remaining from the last lecture? Okay, so we have one last bit left from the last lecture, which is dilated convolution. So what's dilated convolution? If you think about regular convolutional layer, which is here, right? You have a input feature map or input image of 5 by 5, and then let's say that you have a 3 by 3 kernel. If you have a 3 by 3 kernel, and then you have a stride of 1, then your convolved feature, so that's your output feature map. Your output feature map is 3 by 3, right? Then if I ask you, what's the receptive field? What's the collective receptive field? That's a receptive field that pulled together. What's the collective receptive field of this 9 pixels in this output feature map? So what's the collective receptive field? Is it the size of the receptive field? Any thoughts? Yeah, right. 5 by 5, exactly. So if you look at the collective receptive field of this output feature map, it's 5 by 5. That means these 9 pixels, they are looking at this 5 by 5 region in the previous step, right? So this is traditional convolutional layer, but dilated convolution is a little bit different. They kind of dilated or inflate the kernel by inserting more space between the kernels. So if you look at one example of a dilated convolution, so there's a additional parameter here called dilation rate. If dilation rate is 2, then that means you kind of inflate the kernel by a ratio of 2, basically. So let me bring up the pen here. So if you are, for example, if you are computing, so this is the input, so this is the input, and this is the output, okay? Then if you're computing 1 pixel in the output, for example here, then you would need to compute the weighted sum of these 9 pixels in the input. So you can see that it's kind of different from the traditional convolutional layer, right? Because the kernel kind of dilated by a ratio of 2. And by doing this, you can see this animation kind of scan through this previous layer, and again get this 3x3 feature map in the output. So in this case, you can see that the receptive field of this 3x3 output feature map collectively, it gets larger, right? Originally it's 5x5, right? Originally it's 5x5, but now it's like 7x7. So by using this dilated convolution, you're able to get a larger receptive field with the same number of parameters. So this is like free lunch, right? You can look at the bigger picture without having to learn more parameters. Now this is exactly what these two pictures show, right? So this is one dilated convolution, which is equivalent to the traditional convolution. The black box shows the receptive field collectively for these 9 points, right? And this is the 7x7. Again, the black box shows the size of the receptive field. Right? So again, so this additional hyperparameter we call dilation rate. It can be tuned in practice, and if your dilation rate is larger, that means you're going to get a larger receptive field, basically. And you can see, again, comparing these two, you have a larger dilation rate. Although you have the same number of parameters, you get a larger receptive field. Okay. So this is one last bit from last lecture, is dilated convolution. Any questions so far? Empirically, of course, when people first propose this, they definitely observe performance improvement, and especially when they compare network of the same size, like the network with the same number of parameters, and the dilated convolution works better. Right. But it's actually less frequently used nowadays, because these days people tend to basically stack more layers to get larger receptive field instead of using this kind of dilated convolution, because you can afford larger memories, basically. And another downside of this dilated convolution is that it's particularly demanding in terms of padding. You can see that you're kind of dilated this kernel, and in order to, sometimes you would like to keep the same size of your feature map, right? You need padding, and you can see that if your input is 3, then your output is your input is 7, then your output is 3, right? So that's gonna be shrinking the feature map size quite a lot. And sometimes, if you want to keep the feature map size, you would need to pad a lot, like on the peripheral, in order to get the same feature map. So that's another, I would say, disadvantages of dilated convolution. Yeah. Cool. Good questions. Any more questions? Okay, so this is dilated convolution, and to end our convolutional network lecture, I would like to briefly go through a PyTorch workflow to basically build a convolutional neural network. So this is going to be also related to our homework too, and For those of you who are already very familiar with PyTorch, so this is going to be very, very easy. Okay, so this is the PyTorch tutorial telling you how to build a new convolutional neural network. It starts with importing all the packages, but we're going to ignore this for now. So we're going to go directly to the key part of this code, which is to build a convolutional neural network. So usually in PyTorch, you're gonna have a class, right, because it's based on Python. And inside this class, there are two methods that are most important. The first method is the initialization method. The initialization method is going to be the system would automatically call this initialization method if you knew a class, right? You will create a class, right? And in this initialization method, you're gonna basically create a lot of layers that are needed in your convolutional neural network. So you can see that this is to create the first convolution layer. This is create the max pooling layer. This is to create the second convolution layers, and you have 3 fully connected layers here. So when PyTorch is running these lines, for example, when PyTorch is running this line, that means PyTorch is creating an object, and inside this object, you have different parameters. Inside this object contains the parameters, basically all the kernels of these convolution layers, right? It also contains the gradient. Basically, it has this placeholder to contain the gradient of these parameters as well. Okay, and this is all the layers. And the second important method is the forward method. So in the forward method, you're basically gonna connect all these pieces together, right? You're gonna have you can see what it says is that you're gonna the X is gonna be your input, and your input is gonna go through the first convolutional layers, and then it's gonna go through the ReLU. And the ReLU you don't need to define in the initialization because ReLU doesn't have any parameters. And then you're gonna go through the pooling layer. So this finishes basically the first convolutional operation, and you get X. So and then you're gonna feed this X into the second convolution layers, and go through the ReLU and go through the pooling, right? And after all this, you're gonna get some kind of feature map, right? It's like a 3-dimensional tensor, and then you're gonna kind of stretch this feature map into some vectors, right? So this is what this flatten function does. It stretch a feature map into vectors, and then you can feed these vectors into some fully connected layer. So after this, it's all the multi-layer perceptron. You're going to go through a fully connected layers, and the ReLU, and fully connected layers, and ReLU, and the final fully connected layer. So this is going to be your output. Okay. And this is basically the most important part in the PyTorch code to create a network. And any very complex network usually is going to create using this code structure. Okay. And then you're going to, so this is the network. This is only the definition of a class. We haven't really do anything. And then we're going to create basically a new object of this class. So when you're calling this line, basically it's going to automatically run this initialization method, right? It's not going to do the feed forwarding yet, but it's going to create all these layers with the parameters. Okay. And then what you're going to do next is that you're going to define the loss function. So all this it only tells you what the network is, right? Remember, in machine learning, the important thing is what the model, the objective function, training algorithm, and data. Right? So this gives you the model, and the loss function is defined actually here, right? And the training algorithm is defined here. So basically, we're going to use SGD, stochastic gradient descent, as the learning algorithm, right? And then basically, after all this is defined, you're going to train the network. So how do you train the network? Usually, the network is trained by going through the data set one pass after another pass, right? So this is one pass of going through the data. We call it epoch. So in here, we're going to loop over 2 passes. So basically, the total number of epochs will be 2, and this is running loss. So basically, in this second for loop, what this second for loop does is that it's going to fetch one mini batch after another, and then it's going to feed forward to the neural network, compute the gradient, and then update the parameters. So this I is the index of the mini batch, right? And data is the mini batch, right? So if you fetch the mini batch of data, right? So you can see that it fetches a mini batch of data, and each mini batch of data, it has a batch of x and it has a batch of y, right? So this is the x, this is the y. And then you're gonna clear the gradient, and we're gonna talk about this next in more details later. So you're gonna clear the gradient, and then you're gonna do the feed forward thing. So this is your x, right? Your x is gonna be feed forward into this network. So when you call this line, when this line is run in PyTorch, basically it's gonna run this function. Right? It's gonna use x as input and go through all of this to output the network's prediction, basically. So this is gonna be your output, and then you're gonna compare your output and your labels, right, to compute the loss, and then you do the backward. When doing the backward, this is exactly like what we have discussed in the computational graph. When doing the backward, it's going to go from the loss backward to all the parameters, to compute the gradient of all the parameters. Right? And then you're going to do this optimizing step. So this step means that you are actually performing one step of gradient descent. Right? You're going to perform when you do backprop, what you get is the loss with respect to W, right? And when you do the step, you're doing something like this. You have the learning rate, say learning rate is rho, and so when you do the step, this is what the step does, right? So this is what actually modify the parameter, okay? And then you're going to basically track the loss. So because in each round, right, you're gonna compute the loss. So we're gonna basically add this into a history to check if the loss is really decreasing or not. And you go back, basically loop through all the mini batches in the data set until it reach the end of the second epoch. So this is it. This is the training process of a convolutional neural network. Now let's talk about why you need to clear the gradient. This zero glad. Anyone know why you need to clear this gradient? Any thoughts? Or do you usually just, like, if you're using PyTorch, you just follow the workflow and clear the gradient as usual, but you actually don't know why? The previous gradient is removed. So what you said is that the gradient is accumulated by default. So you need to clear it up. Yeah, exactly. So when the PyTorch is this PyTorch system, it's built such that when you're doing the backprop, when you call this backprop, what it does is not just compute the gradient. Because you have, let's say that you have this computational graph, right? You have this W and you have this X, and then you compute the loss, right? And in this node, in this computational graph, it's going to have, for example, it's going to have a W, or w dot parameter. So this is the parameter, right, of w. You also have this w grad. So this is the gradient of the parameter. It's also stored in the system. And when you do backprop, what it does is that it's going to accumulate the gradient. So this h grad is going to be accumulated into this system. Okay, so it's going to accumulate it. It's not gonna directly set the gradient to your computed gradient. It's going to accumulate it. That's why you need to clear it first, because otherwise, when you're doing backprop for the next, right, when you're doing backprop for the next iteration, you're gonna get all messed up, right? You're gonna, if you do not clear it and you accumulate the gradient, if you go through the next iteration and you do the step, then in the next iteration, it's gonna it's equivalent to update the parameter twice, right? So this is a minor detail you might need to take care of. Okay. So any questions so far? So this is a very brief introduction, and in the homework there will be more details, and I'm sure after reading the homework and finishing the homework, you will get much more familiar with the workflow of PyTorch if you haven't already. Okay, and you can see that after running this block, right, we're gonna see that the loss is actually gradually decreasing, right, and finish training. So this is epoch 1, 2000 iteration. So in the 2000 iteration, the loss is 2.2, and epoch 1, 4000 iteration, the loss gets smaller and smaller, right? And after you finish the 2 epochs, then your loss decreased to 1.3, which is good. Okay, so after doing this, we can actually try to see what happens. So this is a Cypher 10, so it's a data set with 10 classes of images. And after doing this, we can see how it works. We sample 4 images from the data set. You can see that these 4 sample images, the first one is cat. It's very low resolution image. So the first one is cat, second one is a ship, third one is a ship, and fourth one is a plane. So this is our example testing data set. Okay, so now let's feed these 4 images into our network to see what our network predicts. So this is so we already, and in here we already kind of save our network, right, into the disk, into the hard disk. Okay, and now we're gonna initialize the network and load all the parameters into this network, and then we're gonna feed this image into the network to compute the output. So this is to compute basically the logic of the neural network, and then you can see the prediction. You can see that the accuracy is, I guess it's good enough, right? In the first 2 images, it predicts the ground truth class correctly. The third one is not so correct, but it's close, ship and car. And the third one is ship, and the ground truth is plane. Okay. And if you compute the overall accuracy over the whole data set, over the whole test data set, I mean, the overall accuracy is 56%. So it's like half the time you get it correct. Right? And it's actually consistent with our example here. Right? Half of the time you can predict correctly. Right? And this is the code for compute the accuracy for each classes in the images. You can see that when the images is actually a class, it's actually much easier to predict it correctly. Right? And also if it's a flock, right? And probably because it has very distinctive features. But if an image is a deer, or I don't know, if it's a dog, it's much harder to predict. So this is a very brief overview of how to use PyTorch and to build a neural network and train it. So the link is already put have the link in here in the slides. So we're going to update the slides on Canvas so that you can have a check. It might also be helpful for you, if you want, you can also refer to this one when you're doing the homework. Right? And the homework is going to have far more details, both higher layer details and lower level details. Okay, so this is it for convolutional neural networks. And before I move on to recurrent neural networks, any questions so far? Okay, so let's move on to our next part of today's lecture. So it's going to get, if you're not familiar with recurrent neural networks, so this is going to be, I would say it's a little bit involved to understand than convolutional neural networks. So recurrent neural networks. So why do we need recurrent neural networks or RNN? We need recurrent neural networks mainly because we want to model sequences. So you will see why in the next few slides. So sequences are basically everywhere, right? If you think about the nature, right? Naturally, for example, the text that we are reading, for example, we're reading books or we're reading web page, so all these texts, they all come in sequences, right? The text is just a sequence of words, right? And speech, when human talk, when humans speak, so this speech is also a sequence of signals, right? You can, in speech recognition, speech is represented by a sequence of phonemes, right? And video too is a sequence of image frames, right? So it's also sequences, and human genes is also a sequence of genetic code, right? So all of these are naturally represented as sequences. And even if you consider images, like what we have been talking about in the past 2 lectures, and images can also be processed sequentially, right? If you can actually process in images patch by patch or pixel by pixel sequentially. And sometimes this is also what human does, because when humans recognize or analyze some image, it sequentially attend to different part of the image, and then it's gonna kind of try to understand what the image is about. Okay. The use cases. Again, images. So when human or model are recognizing what these digits are, you can actually train the model to sequentially attend to different part of the image, and then you can recognize the image. And this is especially useful when there are multiple images in a scene, right? Because that way the model can sequentially attend to different images, right? You can see that in this case is attending to one of the digit first and then finish it and then attend the second digit. And another use case is caption generation. So the task of caption generation is that if you are given an image and then you want to generate a caption of the image. So a caption is just a sentence, right? And this sentence is actually a sequence of words. So this is, again, sequences. And you can think of this as a conditional generation, because when you're generating this sequence of words, it's going to be conditioning on the image, right? So this is caption generation. It's also about sequences, and that's why you need RNN. Okay. And another case is handwriting generation. When you're generating handwriting, right? Handwriting is just a sequence of stroke, right? Therefore, you can generate one stroke after another, and it's still a sequence model. Paintings too. So if you think about paintings, or in this example, it's oil paintings. Oil paintings is just it's also a sequence of stroke, and it's a sequence of like larger stroke followed by a smaller stroke and smaller strokes, right? And also sequence model. And even when you think about recommender system, when the object that you're trying to recommend is represented as a sequence, it would also be helpful to use RNN too. For example, if you recommended articles, right, if you use a sequence model to model this text, then the model will be more sensitive to the context around each word. So, for example, the same word apple, it might mean different things depending on the context, right? So if you use a sequence model, the sequence model will do a better job in terms of modeling the context of each word and better understand the meaning of each article you want to recommend and improve the performance, right? So here you can see that if you treat the article as a sequence versus if you treat the article as just a bag of words, the performance is actually very different. In this use case, it's like 60% versus 20% in terms of precision. Okay. So these are all these examples. So what exactly is sequence modeling or sequential modeling? Formally and very, very generally, sequence modeling tries to basically learn this conditional distribution of xt given the previous axis, right, in the previous time step, right? So you want to model p of xt conditioned on xt minus 1, xt minus 2, all the way to x1. A typical example would be here a stock index prediction. Right? You're given all the history of the stock index. Can you predict the stock index in the next day, for example? If you can do this, then probably you can make a lot of money, right? So this is another example and a formal definition of what sequence modeling is. So it's a simple example. Okay. So how can we do this? How do we learn or how do we approximate this sequential model? Right? A simple case, if you think about it, right, if you want to predict xt, given xt minus 1, minus 2, all the way to x1, then the simplest way you can do it is to use a regression model, right? You just, for example, train a linear regression model to take all the previous history as input and then predict the current value, right? But there's one problem here. The problem is that the input size is actually different for different t. For example, if you want to predict, let me just, for example, if you want to predict x3, right? Of course, you can say that the x3 is equals to a2 times x2 plus a1 plus x1 plus a0, right? So this is a very simple regression model. You can predict x3, but how about x4, right? If you want to predict x4, you're going to have one more parameter, right? You're going to have x3, x2, x1, right? And another bias, right? And you know that for x2, right? You know that for x2, you're going to use a2, right? And for x1, you're going to use a1, and you have a bias. But how about x3? Right? What's going to be the coefficient of x3? You actually don't know. So when the input size is varying, it's actually very difficult to train a model on previous data and predict the next data. And to cope with this problem, we have this autoregressive model. The autoregressive model says that we would only use the past tau observation to predict the current value. So what it says is that to predict x3, we're gonna use the previous two entries, previous two time step value to predict the next value. So for x3, it's going to be a2 times x2 plus a1 times x1 plus a0. But for x4, we're going to do the same. Only this time x2 becomes x3. Right? So this is going to be still going to be a2, but this time it's going to be multiplied by x3. And still going to be a1, but this time it's going to be multiplied by x2. And then you have this bias term. So every time when you're predicting the current value, you always use the previous 2 time step. So this is in an example of autoregressive model, a very, very simple example when tau is equal to 2. So when tau is equal to 2, it basically says that you only use the past 2 observations to predict the current value. Okay. Any questions so far? The autoregressive model. Exactly. Yeah. The parameter A2, A1, and A0, they're the same across different time steps. Yeah. So only this way can you learn the model that can generalize to future data, right? Otherwise, you're not able to do this. Good question. Good question. So when you're using this, for example, this autoregressive model with tau equals 2, it's basically making the assumption that only the previous 2 time step can affect the current value. Yeah, so this is the assumption. This assumption may not be true, and oftentimes it's not true, but it's a trade-off you have to make, because otherwise you cannot train a model. Yeah. More questions? Okay. So this is very, very, very simple autoregressive models, and we're gonna see that this is oftentimes is not powerful enough. And next, there's a slightly more powerful version of autoregressive model. It's called we call it latent autoregressive model. And in this class, we're gonna briefly talk about this. And this is actually what leads to RNN, recurrent neural networks. But in here, we just want to briefly mention this, why it's called latent autoregressive model. So the problem with this autoregressive model, like what we discussed and what you asked, is that it makes this assumption that you only care about the previous tau observation, right? So this assumption is kind of like the sacrifice you have to make in order to make the model learnable. But what if I don't want to make such assumption? What if I want to, when predicting the current value, I want to take into account all the history, all the past history. It can actually be done, right? It can be done by introducing a variable we call ht. So this variable ht is a latent variable, and this latent variable represents a summary of all the past history. So this ht contains the information before time t, before and including time t, right? And then all you need to do is you only need to learn p of xt given ht. So simply put, you can actually learn a neural network, right? You can actually learn a neural network, something like this, right? This is your x, and the input is going to be your history. So learn a neural network to map the history into the current value. This might not be. So this is going to be, sorry, t minus 1. Okay. So t minus 1 to be exact. So this is learn the history, learn the neural network to map ht minus 1 to predict the current value. So if you can do this, then naturally you can consider the whole past history rather than just using this autoregressive method to consider only the past tail observations. And what's nice about this is that you can use the same neural network, right? You can use the same neural network to predict different time steps, right? So this is to predict st, right? And to predict st plus 1, you can also use the same neural network, right? Okay. Use the same neural network to predict xt plus 1 given ht. Right? And this is one piece of the idea in recurrent neural network. Right? And you can also expand this. Right? This ht minus 1, it contains all the information in the past, right? Then that basically means that ht minus 1, it contains the information from the current time step. So the current time step is t minus 1, right? And it also contains the information before t minus 1. So the information before t minus 1 is summarized as ht minus 2, right? So this is why we have this equivalent equation. So when you're learning p of xt given ht minus 1, it's equivalent to learning p of xt given st minus 1 and ht minus 2. So this is what exactly shown in this figure. Let me bring out the pen here. Right? So if you try to predict ht minus 1, right, then the st minus 1 should contains the information from st minus 2 and st minus 1. It basically summarized the previous information and the current information. And with this st minus 1, you can then go ahead to predict the next value, right? The next value here. So we use a hat to represent, that's our prediction, right? So this is here. So this is actually already a recurrent neural network. Right? You can see that all these things, they are operated in a recurrent way, and all the functions, they are shared across different time steps. Right? For example, when you're predicting st given ht minus 1, you're using the function f, for example. Then you're going to use the same function f to predict the next time step, right? And the next time step also, so on and so forth. So this is a very high level and brief idea of latent autoregressive models. We're going to go with much more details and concrete operation in recurrent neural networks later. But for now, you only need to kind of get familiar with this high-level idea of introducing a latent variable, h of t, to kind of indicate or denote the summary of the past. So this is a history or hidden state. Right. Any questions so far? Okay, so we're going to go, so this is autoregressive models and latent autoregressive model. Okay, so this is actually a very high-level picture of today's lecture. So next, we're going to first go through some autoregressive model first, and then we're going to kind of see why it has some kind of limitation, and then we're going to move on to latent autoregressive model, which is RNN. Okay. So we're going to start with simple autoregressive model first. So this autoregressive model, like what we said, it makes some assumptions, right? It makes this kind of stationary assumption. So what's stationary assumption? The stationary assumption says that basically it says the specific value of xt, it might change, but the dynamics of the time series itself is not going to change. Like here, right? It's basically making this assumption that this x4, it might be different from x3, right? But the relation between, for example, x3 and its previous two observations is actually the same as the relation between x4 and its previous two observations. Right? So it's making this kind of assumption. So this assumption says that the dynamics itself is kind of stationary. And the reason to make this assumption is that if the dynamics, for example, let's say the dynamic itself is not stationary, then you're never going to be able to predict the next value anyway. So you might, in this case, you might as well just assume that it's stationary, and then you train your model to predict it. And statisticians make this argument, and they call that dynamics that do not change. They call this stationary. Right? So if you make this stationary assumption, then you can actually model the droid probability of all the values from the first time step to the last time step, which is xt, using a conditional probability. Basically, it's a product of t conditional probability. You can see that it's basically let me see. So, for example, x1, p of x1, s2, s3 is going to be equal to p of x1 times p of x2 given x1, right? And times p of x3 given x2 and x1. And the stationarity is reflected on the fact that we're using the same t here. We're using the same p here. So whenever you are trying to predict x2 or x3, you're going to be using the same model. Right? And from here, we will kind of try to simplify the model even more to say that if we only care about the past tau observations, then we can think of it as a finite horizon autoregressive model, right? Or finite horizon stationary model, and people sometimes also call it the Markov model. So if the autoregressive approximation is accurate, then we say that the sequence satisfies a Markov condition. So if you're familiar with Markov model, you probably have noticed that there might be different order of Markov model, right? If tau equals to 1, that corresponds to the first order Markov model. The first order Markov model is simplest Markov model. It basically says that to predict the current value, you only need the previous value, right? Nothing more. So this is the first order Markov model. What it says is that in this case, if you want to predict x2, you only need x1, and to predict x3, you only need x2, and you don't need x1 here. So this is the first order Markov model. You can have the second order Markov model, then that's going to be corresponding to tau equals to 2, which is something like here, right? You only look at the previous two observations. So this is the second order Markov model. Right? And this kind of Markov model, for example, the first order Markov model is particularly nice, right? Because if, let's say that xt is a discrete value, then you can actually compute the marginalization. Like for example, given x minus 1, the probability of x plus 1, you can actually compute it by marginalize xt out, right? So what it means is that so p of xt plus 1 given p of t minus 1, right? And to compute this value, what you need to do is you need to, first of all, have this joint distribution of t plus 1 and t, right? Given st minus 1, right? You have this joint distribution of xt and xt and st plus 1, right? And then you're going to marginalize xt out. Right? If you marginalize xt out, then you're going to get p of xt plus 1 given xt minus 1, right? And then inside this summation, you're gonna decompose this probability distribution into two terms, right? So inside this summation, you're going to decompose this as, let me follow the order. So the first term would be p of xt, right, given st minus 1, right? And the second term would be p of st, you have st plus 1 given xt and xt minus 1. Okay. So this is by the trend rule, right, of conditional probability. Right? If you're not familiar with the trend rule, you can just the conditional version of the trend rule. You can pretend that this xt minus 1 is not here. Then if you multiply these two, then it's actually equivalent to the joint distribution of xt minus 1, xt plus 1 and st, right? And then you can add this xt minus 1 back into the right side. So I hope this is slightly more convincing for you. If you're not familiar with it, feel free to check with me offline. So this is kind of a prerequisite. Right? And then you can see that if you're making the Markov assumption, that means you want to predict x t minus 1 or t plus 1. You only need the information from xt, and you can actually forget about xt plus 1, xt minus 1. Right? So that will give you p of x t plus 1, xt, and xt minus. Okay. So this is what's nice about Markov model. So basically, it gives you a kind of like a easier and more efficient computation. Right? Now you only need to compute these two terms and go through different values of st, and then you can add them up to marginalize it out, and then you can get this marginal distribution of x plus 1 given xt minus 1. Right? So using this one, you can actually predict 2 steps ahead, right? Like you not only want to predict tomorrow's stock price, you can actually predict the price in the day after tomorrow. Right? So this is Markov model. Any questions so far? Okay. So this is, now let's move on to another more concrete example. Let's say that you're modeling language. Then you're basically modeling the joint likelihood of a sentence, for example, a sentence of length t. then the joint likelihood of a sentence from W1 to WT, you can actually decompose it, right? You can actually decompose it into P of W1 times P of W2 given W1 times P of W3 given all the previous words, and P of W4 given all previous words, right? So on and so forth. So you can actually use this kind of autoregressive way to model the joint likelihood of a language of a sentence, right? So for example, this sentence statistic is fun, period. So we have 4 words here, 4 tokens here, right? It can be decomposed into the probability of the word statistics times the probability of the second word given the first word, and the probability of the third word, fun, given the first 2 words, right? And the probability of the last token or last word, which is the period, given the first 3 words, right? Statistics is fun. So we can actually factorize it into 4 terms, right? And now comes our Markov assumption or stationary assumption. So in natural language, they call it a different name, which is n-gram model. So in a 1-gram model, the model will only look at the word itself when they are computing the likelihood of the sentence. Right? In a 1-gram model, a 1-gram model is actually equivalent to our autoregressive model or a Markov model where the tau equals to 0. Because you can see that it's actually, when computing the probability of W1, it's actually not conditioning on anything, right? So tau is actually equal to 0. It's conditioned on no previous observations. So this is the 1-gram model, and it corresponds to our Markov model with tau equals to 0. So this is the 0th order. Basically, it's the 0th order Markov model. And if it's a slightly more complicated model, which is a 2-gram model, in the 2-gram model is equivalent to the first order Markov model. So basically, when you're computing the probability of a word, it's going to be conditioned on 1 previous word. So the word that's, so for example, the second word is going to be conditioned on the first word. The third word is going to be conditioned on the second word, so on and so forth. So this is the first order Markov model. And in natural languages, natural language processing is equivalent to a 2-gram model. You can see that when they're modeling these languages, they treat 2 consecutive words as a unit, right? And they model their joint probability. And you can also go further to say that you have the 3-gram model, and this is equivalent to the second order Markov model. So in here you can see that in order to model W3, you're gonna need to condition on W1, W2. Okay, and to model W4, you're gonna condition on W2 and W3. So this is autoregressive language model. It's kind of a more concrete example. Okay. So any questions so far? Good question. That depends on how many data that you have. Right? If you have a 3-gram model, that means your model is more complicated, right? Assuming you have enough data, then yes, it's going to be better. But if you don't have enough data, then you're going to overfit, and the model is kind of worse than the previous one. Yeah, good question. Any more questions? All right, so now this is basically the end of the naive autoregressive model. Again, let's go back to this overview slide. We mentioned that we're going to talk about autoregressive model and latent autoregressive model. Right? So this is the autoregressive model part. We talk about how to use this autoregressive model to for example, how to model languages, right? Now, the problem with this autoregressive model, like I said, it assumes to make the model learnable, it has to assume some kind of stationary or Markov conditions, right? For example, in here, you assume that each word or each value is going to be conditioned on the previous two values. But in this way, it's actually very difficult for the model to actually condition on the whole history. And naturally, we would like to do that, because if the model can condition on all the past history, then the model could be stronger, right, and more flexible. And this is why we need a recurrent neural network, because recurrent neural network does exactly that. It uses a latent state, HT, to summarize the whole history, and using this history to predict the next value. Okay, so let's go to recurrent neural network to see how it works. Like I said, if you use simple auto-regression model and make some assumption to get an n-gram model, you can only see n steps into the past, right? So this is good, but it's not good enough. But if we want to model longer temporal dependency, then we will need to increase n. And like I said, if you increase n, then you risk overfitting, right? According to kind of related to the question, then you're going to need much more data in order to learn your model efficiently and effectively. So it's actually prefer to use the latent variable model, like we said here. So in the latent variable model, we try to model the value of xt given all the past history. We try to approximate this using, maybe it's better to start from this one, using this. So it's kind of try to summarize, right? Summarize all the values, including xt minus 1, right? This one, and we say that all this history, we call it ht minus 1, ht minus 1, and all is left for us to learn is just to learn a p of xt given ht minus 1. So this is what you need to learn. And you can use this model for every time steps, right? So it's actually in terms of neural network, it's actually a shared weight mechanism, right? And recursively, you can compute this xt minus 1 using, so this ht minus 1 is actually equivalent to combining the xt minus 1 and ht minus 2. Okay. So ht minus 2 is the history up to t minus 2, right? And if you combine this with the current data, xt minus 1, then that becomes the new summary of history, right? So this is all very intuitive and natural. Okay. So this is the prediction part, right? So you get your history and you predict the next value. But there's one piece that's left. That is how do you update the hidden state, right? Like what we said, this ht minus 1, it has to be a summary of the current value and further the history further into the past, right? So you will need to be able to update your history. So basically, besides learning this p, you also need to learn another function, which is how to update your history, right? So how do you update your history? By combining the current value and your previous history, right? You need to learn two functions. The first function tells you how to compute this one. The second function tells you how to combine ht minus 1h and xt into ht, right? So this is the first function you need to learn, and this is the second function. So both of them are for the second function. Okay, and this is the high-level idea of a recurrent neural network. Okay, and to be more concrete, a recurrent neural network looks like this. So let's also bring up the equation here. So before I bring up the equation, let's say so this is the input, right? So for example, this can be your x1 and this can be your x2 and x3, right? And you have this hidden layer. So this hidden layer is actually the history that we mentioned, right? This history, for example, this can be your h1 or and this is h2 and h3, right? And this is the output layer. So for now, let's call the output layer. So this is like y1, y2, y3. Okay. So more concretely, let's say this is x1, this is x2, this is x3. Okay. And same here. So this is like h1, h2, and so this is actually needs to be y2. So this is h1. So you can use h1 to predict y2. You're going to use h2 to predict y3, so on and so forth. So this is the overall recurrent neural networks. Now let's talk about how do you compute every node in this recurrent neural networks. Let's look at this equation here. Okay, so to compute, so again, our goal is in recurrent neural network. Our goal is that given all this input x, we would like to compute all this output y. Right? So in the middle, we will need to compute h here. So how to compute h? H is the history containing all the information up to the time step t. So to compute ht, you will need to, like I said, you will need to combine the previous h and the current x, right? So how to combine the previous h and current x? You use some form of linear combination plus nonlinear activation, right? So you put your previous h here, so this is h t minus 1, times a learnable weight matrix. So this is a learnable weight matrix. You can see that this h, right? This h has a dimension of 3, right? And therefore, this weight matrix is going to be a 3 by 3 matrix, because your result of the result of your update is also going to be 3-dimensional, right? So this is the previous history and your current value. So the current value is going to be xt, right? So this is your xt, and xt minus another weight matrix. So this xt here, it's a 4-dimensional vector. Right? Therefore, because the resulting ht is a 3-dimensional vector, therefore this weight matrix is going to be a 3 by 4. Right? It's going to be a 3 by 4 matrix. And you have a bias term, which is also 3-dimensional. Right? So this is how you compute your new history, ht, given your previous history and your current value. Okay, and when learning, and of course after all this linear combination, you're going to follow this by a element-wise nonlinear activation. Okay, so this can be the sigmoid or hyperbolic tangent or ReLU. Okay, and we're going to discuss what activation is better next. Okay, so this is how you compute ht, right? And after you compute ht, to predict yt is much easier, right? So here you can just compute or predict yt using ht directly. So how do you do this? You just have this ht and multiply by the weight matrix, add some bias, and go through some kind of nonlinear operation. So in specifically, because we're trying to predict characters here, right? So if you're trying to predict characters here, that means it's equivalent to performing a classification task. Therefore, this f here is something like a softmax operation. We're going to talk about this in a little more details in the later slides. But for now, what's important is that to predict YT, all you need is HT, right? HT plus HT multiplied by some learnable parameters at some bias, right? So this is what's the basic operation in a recurrent neural networks. Okay, so two key steps. One is how do you compute the hidden states, and second is how do you compute the output, right? Any questions so far? You YT to predict. Oh, you mean use the YT to as input to the next XT? Yeah, exactly. Yeah, yeah. This is it's written as a general case, right? And in practice, you can use this to do autoregressive generation. Yeah. We're actually gonna talk about this in a few slides later. Yeah. Exactly. Good question. You don't have explicit control over this because RNN inherently, and it's actually an advantage of RNN, right? Try to summarize the whole history, and there is some more sophisticated model that it can try to automatically learn which part of the history to focus on. By adding some kind of attention mechanism, and we're going to talk about this in the next few slides. A gated version of this RNN, it also somehow has this kind of capability. Right? If you consider gating, that basically means that you are the model is gonna automatically try to decide whether to let this history propagate into the future or not. Yeah, I know it's a bit vague, but you're gonna see more and more of this, and in more and more concrete way, how is it gonna help to improve the performance by adding more and more of this inductive bias. Yeah. But one thing is for certain is that you're not. From this RNN forward, you're not going to explicitly control what the tau is. The model is going to automatically learn this for you. Yeah. Cool. Any more questions? Okay, so this is RNN, and this is the vanilla version of RNN. Right. And again, just to briefly summarize, what's the key here is to compute the hidden state and compute the output. Okay, and there is actually different small variants of this RNN. Right, you can using the same structure, you can actually use it to do different tasks and different input-output mapping. And the simplest one is the one-to-one mapping. So you only have one x, one time step of x, and have one time step of y, right? And in the middle, the green one is h, right? So this is actually equivalent to our MLP, right? So this is h, this is h, and this is y, right? So this is basically a two-layer MLP, right? And another setting is that you have only one x, but you have multiple y into the future. So one example of this is, for example, if you have used a search engine like Google or Bing, if you type one word, the search engine is going to try to automatically complete your query for you, right? So this is one typical application of one-to-many mapping. You input one word, and it's going to automatically complete your query for you. So this is one-to-many mapping. And there's also many-to-one mapping. So many-to-one mapping usually is used to do sequence classification, right? For example, given a sentence, can you classify for me whether this sentence is positive or negative? Is it saying something good or is it saying something bad? Is the Amazon review is positive review or is it actually a negative review? So this is many to one, and we have also many to many. And many to many is also very commonly used. It can be used to do forecasting. It can be used to do machine translation. Right? For example, in machine translation, this is going to be your input sentence. Right? This is going to be your input sentence, and this is going to be your output sentence. So this can be English and this can be French, right? And in forecasting, this can be the stock price for the previous 3 days, and this can be the stock price for the 3 days into the future, right? So this is many to many. And you have another form of many to many. So this is just you have 3x and you have 3y, but they all need to be in the same steps. And this is sometimes also useful. A typical example is part of speech tagging in natural language processing. You're given a sentence here. And it's gonna automatically output the part of speech for each word in the sentence. Whether this first, for example, whether this first word is it an object or a subject, or is it a verb, right? Or is it a proposition? So this is called post tagging, right? Part of speech tagging, and it's also a very common task. So you can see that although they are all RNN, but depending on how you structure the input and output, it actually corresponds to different setting and different tasks. Okay. Before I move on to the example, any questions so far? I'm sorry? Mm-hmm. XT to 0. Mm-hmm. Mm-hmm. XT. You mean set this one to 0? Or what? Oh, you mean one to many or many to one? One to many, right? Or you want to by H2? Do you mean this one? Yeah, good question. So in here, to calculate H2, you're gonna set x. Basically, yeah, like what you said, the x needs to set to be 0. Yeah, and to calculate H2, basically it only needs to use H1 as input. Yeah, and you can see same here, right? Many to many. Right? In this, to compute this, you only need the previous hidden. You don't need the input. Yeah, that's a good question. Cool. Any more questions? Okay, so this is different settings, input output structure of RNN, right? And this is actually very general, right? Because, for example, we're talking about the vanilla version of RNN, and even for the gated version of RNN, we're still going to run into different settings like this. Right? And some examples. Like I said, many-to-many setting. In many-to-many setting, one very typical example would be machine translation. Right? In machine translation, you're given one sentence, so this is your input, right? And then it's going to output another sentence with different languages, right? Many-to-many setting. And also dialogue generation, which is somehow also very similar to translation, because and in here you're inputting one sentence. Imagine you're talking to an agent, and it's going to output another sentence, right? And here this model is slightly more complicated because it's a multi-round conversation, so you need another layer of hidden edge to serve as a summary of the a dialogue state, right? So the H here is summarize the sentence, but this H here is summarize the higher level. It summarize basically the dialogue state, right? And as they move forward, the dialogue would also move forward. So this particular paper tries to it's like generate a dialogue. It's not. So we can see that after it generates this sentence, it's gonna be used as input, right? In here, and then it's gonna generate another sentence, and so on and so forth. It's also some kind of autoregressive dialogue generation. But the key here is that it's also using the many-to-many structure. Right? And another example is weather forecasting. Right? Imagine that this is the cloud map for the previous 1 hour, and you would like to predict the cloud map for the next 1 hour, right? And you're going to also need this many-to-many structure, because each frame would be one cloud map in the past, and each output frame here is going to be one cloud map into the future, right? And because you want multi-step forecasting, right? You're going to need this many-to-many structure as well. Okay, and so this is RNN, right? And we have a very nice figure here. So you can see that just to review the structure of RNN a bit. So to compute in RNN, again, two most important calculations. One is to compute hidden state, the other is to compute the output, right? And to compute the hidden state, for example, to compute ht-1, you're going to need to use the previous hidden state and the current input, right? And they both go through this function, right? They both go through this function, and this is your h, right? And you're going to, so this is actually also your h, and you're going to use the h to predict your next y, right? So this is your yt. And similarly, to compute ht, you're going to need your ht-1 here, and you're also going to need your xt, right? And then you're going to use the same ht to compute your yt+1, right? So on and so forth. So this is basically just as a review of the RNN architecture. And now let's talk about the difference. Let's say that we're trying to learn a sentence generator or language generator, and there will be some kind of difference between training and inference. For example, during training, how are you going to train the neural network? During training, you're gonna the input to your neural network is gonna be, for example, the time machine by h. Right? So this is the full sentence is the time machine by H.G. Wells, right? And this is just part of the sentence for simplicity. The input is going to be the time machine by H, and the output is always going to be one word, the next word that corresponds to the input, right? So this is the input and this is the output. This is the input time, and the next word served as the output is going to be the word machine, right? And you're going to train the RNN this way, such that whenever you have the input here, right, the RNN would always be able to output the next word, right? If you have the input then the network can output the word time, right? So which is the next word of the sentence. If you have the word time, then the network can output the word machine, so on and so forth. So this is how you train the neural network, because you already have the data set, right? You have all the sentences, so all this input and all this output, they are already given, right? And when training the neural network, you just use, basically it's exactly the same as when we're training a convolutional neural network, right? You have the input, and you feed forward, you compute the loss, and then you backprop to compute the gradient for the parameters you learn, right? And then you update the parameter according to the gradient. So this is the training part. And how about the inference? The inference part is a little bit different. The inference part, because what we want is to generate in an auto-regressive way. So for example, let's say that the task is that we're given the first 3 words, and we're gonna complete the sentence. So this is the task. The first 3 words is the time machine. So let's say that the first 3 words is the time machine. Then you're gonna put these 3 words here, right? And you can see that after your neural network gets trained, you can actually very easily compute H3 here, right? Because you have all this input here. You can easily compute H2, and combining H2 and a word machine, you can compute H3, and then using our output computation, you can compute our Y3 here, right? So you can try to predict the next word here. So let's say that you predict the next word spy. Right? After you do this, you're going to move this word by into the input of the next time step, right here. And then you're going to use the network to predict the next word. Right? The next word is H. And then you're going to move this H as the input, right? So this is H. And then you're going to predict the next word, so on and so forth. And so basically, you're gonna generate the next word auto-regressively one by one. Okay. Any questions so far? What you said is actually another variant of training. Right? So in the training, this is what we do. Right? And what you're saying is, are you saying that during training you always predict the next one word and you train it this way, or what? You can do this. Yeah. If you want to do this, and during training you can actually, for example, you can use our many-to-many setting, right? You can train the model using the many-to-many structure, right? You can use the input. So this is your input, the time machine, right? The time machine, and you kind of remove this, and remove this, and remove this. Right? This is also doable, right? You can, and if you do this, then you're basically training the network such that it can output multiple sentences together, multiple words together. Yeah, it's also doable. And people find that it's more helpful if you gradually change the scheme, because the previous scheme is actually easier, right? Because it's one word prediction, and this scheme is kind of more difficult because it's multi-word prediction. So it might be helpful to gradually change from the one-word prediction to this multi-word prediction. Yeah, and there's many different variants here in terms of how to choose the input and output. Yeah. Cool. Good questions. Any more questions? Okay, so this is RNN, for language modeling during inference, and let's see, what time do we have? Okay, so next before the break, we're gonna also briefly talk about how do you measure your sequence model. So you have a model, right? You have a model to generate words or generate sentences. Right? How do you measure how good your model is? In convolutional neural network, when you're doing classification, it's very easy to evaluate. Right? You just calculate your accuracy in the data set, and the higher the better. But language modeling is slightly trickier, because what you're generating is actually a sentence. Right? How do you measure this is a good model or this is a bad model? And you can actually measure how good, measure the quality of the sequence model by seeing how basically how surprising the text is. If you think about it, if you look at these three sentences, it's raining outside. First sentence. Second sentence is raining banana trees, and the third sentence is raining some random characters. And if your model is surprised, if your model is very, very surprised when seeing this text, that means your model is a good model, right? Because this sentence itself is not a normal sentence, so you should be surprised. And on the contrary, if your model sees a normal sentence, for example, it's raining outside, then your model should not be too surprised, because this is a normal sentence. You should have seen this sentence a lot, right? And how do you measure this degree of surprisingness? Right? You measure this degree of surprisingness by computing the likelihood of each sentence according to your model. If the likelihood, for example, if given your model, if the likelihood of this sentence according to your model is very large, that means the model thinks that it's very likely to run into this sentence, right? That means the model is not surprised. So in this case, it's actually it's a good model, right? It's a good model should not be surprised by a normal sentence. So this is basically the intuition of how do you measure how good a language model is. So basically, we would like to compute the likelihood of all the true sentences or true sequences in the validation or in the test set. We assume that all the true sentences in the validation or in the test set, they're all very normal sentences. So when you're computing the likelihood of these sentences, the likelihood should be high, right? Otherwise it's not a correct model, right? But one tricky thing is that sentences, they have different lengths, right? And if you have a longer sequence, then the likelihood is going to be, so the likelihood is going to be the product of many terms, right? If you have 3 words, then it's going to be the product of 3 terms. If you have 4 words, it's going to be a product of 4 terms, right? Therefore, if you have a longer sequence, that means you have more terms in the product. That means your likelihood is also going to be smaller, right? So this is actually not a good metric if you want to directly compute the likelihood, because the longer sequence, that means it's going to be a smaller likelihood. So what we want is that we want a metric that looks like the likelihood, but we also want it to be agnostic to the sequence of the length. That means we need something like an average of likelihood, right? And this is one of the intuition behind this matrix, what we call perplexity. So the perplexity, if you look at this perplexity, is basically computing the likelihood of the sentences. Right? So this term here is actually corresponds to what is equivalent to the log likelihood. It's equivalent to the log likelihood of xt minus 1 all the way to s1. So basically, and it's the log likelihood. And you can see that if the sentence is longer, then the number is going to be smaller because you have more terms. That's why you need to average them out. So we're going to have this average over the number of words here. So in this way, a sentence with a larger length is no longer has a smaller likelihood. Right? So this is the perplexity. And intuitively, if you look at this matrix, if let's say that you have a sentence of length n, now the length is fixed. If you have a higher likelihood, if I have a higher likelihood, that means this whole thing, right, this whole thing is going to be smaller, right, because we have a minus sign here, right? Then that means what's inside the exponent is smaller. That means the whole perplexity is going to be smaller, right? So we all know that a higher likelihood is better. So correspondingly, a lower perplexity means that you have a better language model, right? And perplexity basically means you can think of it as how confused the model is. This is literally what perplexity means. But basically, if the model is less confused, that means the model is better. If the model has lower perplexity, that means the language model is actually better. Okay. So to summarize, you can use this perplexity to measure how good your language model is. You just take every sequence, every true sequence in the validation data set, and you compute the perplexity and you take the average. Right? So this equation is the perplexity for one sequence, right? And then you're going to compute the average of all the sequences. Okay. Any questions so far? The idea is to use average log likelihood, basically, to measure how good your language model is. All right. Let's have one more thing, and then we're going to take a short break. Okay. So we talk about natural languages, right? And we talk about natural language generation. And if we want to generate natural languages, basically what we're trying to generate is one of the words in the vocabulary, right? And assuming your vocabulary have a size of 1,000, that means you're basically, when generating this word time, you're actually picking one word out of a vocabulary of 1,000 words, right? So that's equivalent to a classification problem, right? It's equivalent to a 1,000 class classification problem. And in a classification problem, how do we represent a table? We represent the table, we represent the label, using a one-hot vector, right? So this is exactly the same. Right? We represent the generated word using a one-hot vector. So in the one-hot vector, only one of the entry is 1, and all the others are 0. So again, imagine you have a 1,000 the size. The vocabulary is 1,000, then only one of the entry is going to be 1, and all the others are going to be 0. It's going to be a 1,000 dimensional vector, okay? And basically, you're going to represent each word as a one-hot vector, and when you're computing the feed forwarding, and this is going to be your O, right? This is your output, and you are going to, so this dimension of this O is going to be, for example, if n is 1,000, right? Then the dimension of O is also going to be 1,000, right? And this 1,000 vector, dimensional vector, is going to go through a softmax, right? It's going to go through a softmax layer, and then it's going to go through the cross entropy, the computer cross entropy loss against the ground truth, and this is going to be your loss. Right? This is going to be a loss to train the recurrent neural network. Right? Okay, so this is the basics of RNN. So let's take a 10-minute break. We can resume at 2:07. Testing, testing. Okay, let's get back to class. Please come back to your seat. Okay, so we talk about the basics of recurrent neural networks. So by now you should be able to kind of see what normal recurrent neural networks does, right? So they compute the hidden state recursively, and then they use the hidden states to predict the output. And they have this weight sharing mechanism, a little bit similar to convolutional neural networks, because if you look at this this equation here, right? So as I said, for every time step, they are going to use the same parameter weights, right? Parameter weights W, right? So this is actually another form of weight sharing, and this kind of weight sharing can sometimes cause problems because you are basically multiplying this weight matrix many times, right? If your sequence is very long, like 100 time step, then it's like you are multiplying this same matrix 100 times. So then you're going to run into the same problem of gradient vanishing and gradient explosion. Exactly like what we have been experienced when in the old days you train a very deep neural network. It's not going to be trainable because you're going to run into explosion and vanishing problem. So now we're going to analyze this in the context of recurrent neural networks. Okay. So the first thing to note is that when we talk about the ReLU activation, we say that nowadays ReLU are more popular, especially in convolutional neural networks. But sigmoid and hyperbolic tangent or tangent H is actually not completely useless because, as we mentioned before, it's going to be useful in recurrent neural networks. So as we promised, now we're going to go through the details on why in recurrent neural network it's actually not a good idea to use ReLU, and instead it's actually a better idea to use hyperbolic tangent and sigmoid. Okay? So the reason is that this ReLU is kind of standard for MLP, right? It's standard for MLP and CNN, but it's not for RNN. The reason is that this ReLU is actually unbounded, right? Because it can get arbitrarily large. And unlike sigmoid or hyperbolic tangent, the output of sigmoid hyperbolic tangent is limited in some range, so you can kind of prevent the explosion of a recurrent neural networks. And to give you more details, let's do a very simple analysis. So we already know that to compute some step, right? Compute some time step, the hidden state in some time step. Let's say that is HL. To compute HL, we're gonna have to, for example, we're gonna take the previous history, right? HL minus 1 times a matrix and plus W times X. So we can basically think of this as a XL, okay? So this is the current input and previous history, right? You take the weighted combination of the past history and the current input, and you're going to go through some activation function here. So G is your activation function. So this is how we this is to write down the equation of the hidden states in each time step so that we can analyze it. Okay. So this whole thing, this very, very long term, is H sub L minus 1. Okay. And you can actually compute H L minus 1 recursively, right? So H L minus 1 is actually equal to U times H L minus 2 plus W times its own current input, right? So this is again some transformation of XL minus 1. Okay, and going forwards, very similarly, you can also expand this L minus 1, right? To compute L minus 1, HL minus 1, you can compute the multiplication, the product of U times H minus 3, right, plus W times its own current input. So this is this whole thing is just to explain for you why this equation makes sense. Okay, so this is one way of writing our hidden states in a particular time step. So before I move on, I want to see if there's any questions for this particular equation. Does it make sense? So a lot of our analysis is going to be based on this equation. Okay. So now let's move on to see what's going to happen, right? Let's say that for simplicity, if we use linear activation, so that means we're not going to have nonlinear activation. And if you use linear activation of G of X equals to X, so that means we completely remove the nonlinear activation, right? If we do this, then this equation can be simplified to something like this, right? It's basically very similar. You just remove all the function G's, right? And you can see that now you kind of gradually see the pattern. Right? You can kind of combine different terms, right? You see all this U here, right? So it's actually going to be equivalent to a sum of L terms, right? The sum of L terms. So you can see that the first term of this L term is going to be a product. So basically, you multiply. You take the product of a lot of U's. So this U's, they're actually the same matrix. You just multiply for many times, and here you multiply for L minus 1 times, and then you multiply it by W and X1. Okay, so this is your first term, and the second term you're going to do the similar. Only this time you're going to multiply for L minus 2 times. Right? So it's 1 time less, right? And times W and times W2 all the way. You can do this similarly all the way to the last term. So the last term you're going to multiply the matrix U for 0 times. That means you get nothing, and then you're going to multiply by U and multiply by XL. Okay? So this is our second line. So if you do not have any nonlinear activation, then this is how you write HL in terms of the input only, right? So you can see that we basically expand everything related to H. So we write HL in terms of inputs only. So these are just X1 all the way to XL, right? Without any H's. Right? And then you can try to write it write this one in a more complex form. So this is basically rewriting this as a summation. Right? So in here, you can see that the HL is actually a sum of L terms, right? Like what I said, is sum of L terms, and then each of these terms is going to have many H, the product of many U's, sorry, many matrix U's, times W, times X. Okay. Now, what decides whether this recurrent neural network is going to explode or not is really this term inside the summation, right? Because this part is really risky, right? Because you multiply U for many times, right? And there's a very high risk that it's going to explode if you do not have some kind of non-linear activation after each application of U to squeeze it such that it's going to become between 0 and 1, and it's very easy to explode, right? In this case, and you can imagine that if you use ReLU, because ReLU is all ReLU does is that if it's negative, it's going to be 0. If it's positive, it's going to keep the same value, and there's always going to be some of the entry that is always positive, and it's going to get very unbounded and very large. Right? So in this case, it's actually not a good idea if you use ReLU, right? To make sure it's bounded, it would be best if you can use the sigmoid function or use the hyperbolic tangent. Right? If you use the sigmoid or hyperbolic tangent, then you can see that after each operation here, the network is gonna go through the nonlinear function G here, right? So there's a lot of steps here that can try to make sure that the output is going to be between 0 and 1, or -1 to +1. Right? So this is why it's a bad idea to use ReLU, and we explain it in terms of the feed-forwarding path. And okay, so this is the first part of the analysis. So during feed-forwarding, if you use ReLU, it's gonna explode, and the solution for this is to use sigmoid or hyperbolic tangent to keep it bounded. Okay. And next, we're gonna analyze why this is still not enough, because even if you do this during backprop, you might still run into other problems, for example, gradient vanishing. But before moving on, let's see if there's any question for this part. Anything unclear? Okay. No questions? Okay. Cool. So this is feed forwarding. Now, feed forwarding, it has a risk of exploding. If you use sigmoid and hyperbolic tangent, you can prevent this. Now let's analyze the back propagation. Okay. During backprop, what's going to happen? If you only have this nonlinear activation of sigmoid and hyperbolic tangent, even there's no problem during feed forwarding, there might still be problem during backprop. And why is that? So we're going to analyze this. So recall this equation, right? This is the same equation as before, right? Same equation as before. Right. And now let's analyze the gradient. Right? The gradient of some of the hidden state in some time step with respect to so this is basically the input in some previous time step relatively far away. So this is like you have a recurrent neural network. So this is your h, right? This is your h. So we have all the x here. For example, this is your x1, this is your x2, this is your x3, this is x4, right? And this is your h1, h2, h3, and h4. And what this gradient says is that I would like to compute the gradient of this one for example, with respect to this one. Right? To compute the gradient of this h with respect to some x very, very far away into the past, what you can do is that you can rely on the train rule, right? So this is the train rule that we are using. So this gradient is going to be a product of three terms. The first term, what's the first term? The first term is the gradient of this h with respect to the corresponding h in the previous time step. So the first term is basically the gradient of h4 with respect to this h1. So this is the gradient of small, just to make it more concrete. It's the gradient of h4 with respect to h1. Okay. And what's the second term? So the second term is, you might be confused here, right? If you look at the second term, there's this h, and there's this h with an underline. So what's the difference? The h with an underline, basically it refers to the hidden state, but it's a hidden state before the nonlinear activation. Okay, so this is a hidden state before the nonlinear activation. Okay, so this is the second term. This is the second term. So the second term. So basically around here, right, inside here, there's a linear version of it. So you have another term which is h8 h1 underscore. But this term is not that important because we already make sure that it's bounded, right? And then the third term would be the linear version, so of this one, right? With respect to h, x. Right? So this is going to be this gradient, right? So this is going to be h1 underline with respect to x1. Right? So to compute the gradient of h4 with respect to, for example, x1, right? You will need to compute three terms. So this is h4 with respect to h1 times h1 with respect to h1 underline, right? Times the gradient of h1 underline with respect to h1. Right? So these two terms, they are relatively simple because they are just two terms, right? Right. So this h1 and h1 underline, they are both in the same time step, right? So it's just one term, right? And this h1 and x1, they're also within the same time step, so it's also just one term. These two terms, basically, if you have 100 terms, right? And what's the most important part is what's here, because this is potentially going to be the product of many terms. So what's most risky is when you're computing this first term, you're going to run into some issues of gradient vanishing or gradient explosion. So for now, we can first safely ignore these last two terms and focus our analysis on this term. So this is why in the slides here, we focus on the analysis of term A here. So term A here is exactly what we're mentioning. Right? So this is the term that we care most about. Okay? Then you can actually further decompose this term using train rule, right? Using train rule, you can see that it's going to be the product of many terms. And for example, the first term will be HL. So this is going to be HL1, right? And the gradient of HL1 with respect to HL1, but before the nonlinear activation, right? So this is the first term. And the second term is going to be HL1 before the nonlinear activation with respect to HL1 minus 1, right? So this is the first two terms, and you're gonna do something similar, right, to go backwards. So this is the HL minus 1, and the same time step, but with different, but without the nonlinear activation. And this is L1 minus 1 to L1 minus 2, right? Going one step after another. So concretely, if you look at this one, so it's equivalent to saying this gradient is going to be equal to H4 and H4 before nonlinear activation times H4 before nonlinear activation with respect to H3, right? And times H3 and H3 without nonlinear, and H3 and H2, right? All the way back until you reach H1, right? So this is a more concrete version of what's on the slides. Okay. Now, so this equation A can be factorized into a lot of term B's and a lot of term C's, right? Now, if you look at all these term B's, what are all these term B's? These term B's, they're actually the gradient of your nonlinear activation. Right? If you use sigmoid, then the gradient of this sigmoid would be sigmoid times 1 minus sigmoid, which is going to be in the range of 0 and 0.25. If you use hyperbolic tangent, then the gradient of the hyperbolic tangent is going to be 1 minus the square of hyperbolic tangent. So which is going to be what? Which is going to, because hyperbolic tangent is between minus 1 and 1, right? Therefore, this whole thing is going to be between 0 and 1, right? Therefore, the gradient is going to be also going to be before 0 and 1. So these are bounded. Right? So these terms B's, they are bounded. Right? So basically, you can rewrite this term in a more compact form into this equation, right? So it's going to be a lot of terms. So this is term B. So and this is term B, right? This is term B. And how about term C? Term C is the H before nonlinear activation, right? And you're going to compute its gradient with respect to H, to the previous H. So that's basically this one, right? That's going to be the matrix U, right? So the term C is exactly the matrix U here. So you can actually rewrite all this gradient as the product of all these terms, right? How many terms are there? That basically depends on how many steps forward do you want to compute the gradient, right? And if you look at this one, you're going to see that it's going to has, if I further analyze this one, okay? So this is one of our very important intermediate results. So remember this one, and then let's go to the next slide, okay? So this is our previous important result. Now, before I move on, let me make sure there's no problem with deriving this part. Any questions so far in terms of arriving at this equation? Any questions? So intuitively, it's going to be, because you're computing the gradient several steps forward, so there has to be a lot of terms, right? If you compute gradient 3 steps forward, then that's going to be the product of at least the product of 3 terms. Right? So this is inevitable. Now, if you look at this equation, this is the key term of our gradient. If we look at this equation, if your activation is linear, right? If your activation is linear, then the gradient is very simple. The gradient would be you just directly multiply the matrix U for L1 minus L0 plus 1 times. So in this case, it's going to be multiplying the u for 3 times. So u times u times u. And you can see that this is very similar to our analysis when we are when we're analyzing the gradient explosion and gradient vanishing, right, in our multi-layer perceptron. Right? So if u is too large, then if you have a lot of steps, you're gonna get gradient explosion, right? But if u is too small, then you're gonna get gradient vanishing. So this is a linear case, and the nonlinear case, it's gonna be slightly more complicated. We're not gonna discuss this in detail, but we're just gonna briefly go through the process and give you the conclusion. Okay. Let's just ignore this one. So, if the activation is nonlinear, then you cannot ignore this term in the middle here, right? But then, in order to make it manageable, you will need a special trick. So that's called eigen decomposition. Basically, you would need to decompose this matrix U into the product of 3 terms. So this 3 terms, this Q here is a very special matrix. It's an orthogonal matrix. So what orthogonal matrix means is that if you multiply Q by Q transpose, it's gonna be an identity matrix. Okay. And S here is gonna be your singular values or eigenvalues, right? And it's gonna be a diagonal matrix, and each entry in the diagonal matrix is your eigenvalue. Okay. So basically, if you and for every matrix U, you can always find a decomposition such that it has this form. Okay. And after you do this, then what's next is that basically in each term inside this product, right, you can basically rewrite these into the product of. So this is basically the same thing, right? This is basically the same thing in the first term, and the second term you basically decompose U into 3 matrices. Right? So if you look at this, then you can see that because this first term here is actually a diagonal matrix. If it's a diagonal matrix and this S is also a diagonal matrix, then you can actually move this diagonal matrix inside this decomposition. So by doing this whole thing is going to be equal to Q times this diagonal matrix, right? And times this other diagonal matrix. So this is the diagonal matrix that contains the singular values, and times Q transpose. Q inverse. Okay. So why is this useful? This is useful because if you multiply a lot of these terms, then a lot of Q's, they are going to get canceled out. Right? If you look at the blackboard, you have this Q, right? And you have something in the middle. You have something in the middle, and you have Q inverse. Right? If you multiply a lot of these terms, for example, you multiply another term, right? Another term of Q, and something in the middle, and Q minus 1. What you're going to get is that you can actually cancel this out, right? Because these are Q inverse times Q, right? So this is going to be an identity matrix, right? So this whole thing is going to become Q times this middle thing, right? By 2 times, right? And times Q inverse, right? So this middle term is exactly what we're showing in here, right? So this middle term is also very easy to compute because this middle term here, right, it's a diagonal matrix, right? So if you raise the diagonal matrix to the power of 2, then just simply raise each entry in the diagonal matrix to the same power, right? And the rest of it is a little bit complex analysis, and ultimately you're going to reach the conclusion that if the largest eigenvalue of U is larger than some value, then the gradient is likely to explode. And if it's the largest eigenvalue of this matrix U is actually smaller than some value, right, then the gradient is going to vanish. So between this one and this equation, there are some very complicated analysis. So we're not going to go through the detail in this lecture, but just note that there is a risk, there's a very high risk of gradient explosion and gradient vanish in the vanilla recurrent neural network, right? Because you can see that if the largest eigenvalue is too large, then it's exploding. If it's too small, then it's vanishing. And the only case where it's going to be stable is that when the eigenvalue is exactly exactly 1 over lambda, right? So this lambda is basically the upper bound of the gradient of the nonlinear activation. This is not very easy to achieve. You need the largest eigenvalue to be exactly arriving at this one value. It's not very easy to achieve. So that's why in the old days it's actually very difficult to train a vanilla recurrent neural networks. Okay, and if you're interested in more detailed analysis, feel free to go to this very classic paper. Okay. So any questions so far? In terms of the intuition, right? The intuition is that the eigenvalue cannot be too large, it cannot be too small. If it's too large, it's going to explode. If it's too small, it's going to vanish. Okay. Questions so far? Okay. If it's not, let's move on. Again, if you're interested, feel free to go through this paper. And so we have this gradient vanishing problem, we have this gradient explosion problem. And one simple trick that people usually use to kind of mitigate this gradient explosion problem is called gradient clipping. So this gradient clipping is a very simple idea, right? It's basically if the gradient norm is too large, then we're going to renormalize it. We're going to renormalize it such that it's going to have a L2 norm of at most tau, right? So let's explain this gradient clipping, right? So this is the gradient that let's say that during backprop, you compute the gradient, your computed gradient is going to be this large. Let's call it delta, right? If delta, this gradient, if the norm of this gradient is smaller than or equal to tau, then you don't do anything. You just keep the gradient. Okay? But if the norm of this gradient is larger than tau, then what you're going to do is you're going to renormalize it such that it's going to be the norm becomes tau. Okay? So first of all, you're going to divide this gradient with the L2 norm of this gradient. So after doing this, the gradient of this, the norm of this thing is going to be 1, right? Because you already normalize it by dividing its L2 norm. And then you're going to multiply tau here. So after you multiply this tau, the norm of this whole thing is going to be tau. Okay. So to give you a concrete example, let's say that you are computing the gradient. You're computing the gradient of some parameter, and the gradient is 1 and 1. So this is your gradient is 1 and 1. So this is 1 and 1, right? And let's say that you set the tau to be 1. So if the norm goes over 1, you're going to use gradient clipping to clip it such that it has a norm of 1. So what's going to happen? You know that the gradient has, so if you compute the L2 norm, right? You compute the L2 norm of this 1, 1. Right? The L2 norm of this 1, 1 is the square root of the first entry square plus the second entry square, so this is going to be the square root of 2, right? And it's actually larger. It's larger than 1, right? It's larger than 1, therefore you need to clip it. So how do you clip it? You clip it as, this is a clip version. The clip version would be your O gradient over your norm, right? And times 1, right? Because you set the tau to be 1, right? So this is going to be your clipped version of the gradient, and ultimately what you're going to get is 1 over and 1 over. So after clipping, this is your final gradient, and then you're going to use this gradient to update your parameter, right? So this is gradient clipping. It prevents very large gradient. If you know that if you have a very large gradient, then this whole thing is going to explode. It's going to move your parameter to a very, 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 very strange place, right? And the loss would be also very, very large, or even very, very small. Okay. So this is gradient clipping, and gradient clipping can help you to prevent explosion, but still it cannot help you to handle this gradient vanishing problem. To handle gradient vanishing problem, you will need a gated version of RNN. So these are the modern version of RNN. So before we move on, let's see if there's any questions in terms of this gradient clipping thing. Questions so far? Okay. If no questions, let's see if we can finish the first gated RNN in this lecture. So modern RNN, the key motivation of modern RNN, like long short-term memory model or gated recurrent units, the key motivation is to make the recurrent network easier to train, basically, and concretely we want to kind of lower the risk of gradient explosion and gradient vanishing. And next, we're going to first describe some very high-level advantages of this modern RNN. So modern RNN, specifically, we refer to this gated RNN. These are RNNs with some gates. We're going to talk about what gates means later. But for now, let's discuss very briefly the inductive bias of this modern gated RNN. The first inductive bias is that this gated RNN has this ability of long-term memorization, and this long-term memorization, because if you look at our previous RNN, right, if our vanilla RNN, it's very easy to vanish after many time step, because you're multiplying the same matrix many times. If the matrix is very, very small, then your memory kind of vanish, right? So that's why vanilla RNN is actually very difficult to handle long-term memory. But modern RNN, with the gating mechanism, it's able to really handle long-term memorization, and this is very important. For example, if you want to train an agent in terms of generating a conclusion in a paper, the paper is very, very long, right? You would need to memorize the content from start to end in order to generate a informative conclusion. If you only have a very vanilla RNN, then when you read the paper to the end, you only remember what's in the paper. Maybe you only remember the last section of the paper, and you're going to write the conclusion only about the last section of the paper. So that's not going to work. So to have a better agent of writing the conclusion in the long, very long sequences, you will need to handle long-term memory well. Right? So this is memory, one of the inductive bias. And the second inductive bias in gated RNN is sometimes it's useful to skip some of the input. Right? For example, if you are training an agent to analyze HTML code, so some of the tags in the HTML code are actually not useful. Right? It would be helpful if you do not waste memory to handle this auxiliary HTML code and just ignore it. So gated RNN has this advantage of skipping input. Right? And the third inductive bias is gated RNN has this capability of resetting the input. So for example, if the task is just to summarize the last chapter of a book, then it will be helpful if your RNN can have this capability of resetting your memory whenever a new chapter starts. Right? So this gated RNN has this capability of resetting things. Okay. So this is the third inductive bias. So these are all very high level idea and what gated RNN can do. But next, let's talk about something more concrete. So this is a very commonly used gated RNN. This is called long short-term memory model. And this model have the capability of achieving exactly these three inductive bias. And we're going to see why later. So what's LSTM and what's the basic idea? And I guess the most important idea of LSTM is, one of them is that it explicitly separates the memory states and the output states. In the original RNN, right, we only have this hidden state H, right? But to handle this long-term memory and short-term memory, we would, as LTM model decides to have two states. The one is called cell states, and the other is called output states. Sometimes we also call it hidden states. So this cell states, CT, it contains the overall history. So this is going to be the overall history from start to end. So this is the cell state. And the output state, it contains only the part of the history that's relevant to predict the current value. So this is the output state. So it kind of separates long and short-term memory. You can think of this C as long-term memory and this H as something like a short-term memory. Okay. So this output state is a small subset, right, of the memory state. And now only the output state is going to be visible to other part of the network. Okay. So the cell state is like the internal long-term memory. Okay. Then if you look at our vanilla, right, our original RNN, right? So this is our original RNN. In the original RNN, it's actually very, very simple compared to this LSTM model, because in the original RNN, to compute the hidden states, the H in each time step, you only need one equation. You only need this equation specifically. You take the current input, you take the past history, right, and you compute that weighted average, weighted sum, right, and go through some linear, some nonlinear activation, and this is your H. It's very, very simple. But in LSTM, things are much more complicated, because you kind of now we have two states, right? You have the cell states, and you have the output states. So you have to compute it separately, and to compute it, so to compute the cell state, we need two steps. Right, let's go through these steps one by one. The first step is to compute a candidate cell state. It's not cell state, it's a candidate cell state. And the candidate cell state has two things. It's going to take the current input, right, xt, so it's very similar to our old LSTM. And it's going to take the previous final states. Right? So it's going to be the previous final states. And it's also very similar to this one. and this is the bias term. So this is the candidate cell states. After computing this candidate cell states, we're going to compute the final cell states at the same time step. So the final cell states, it's a weighted sum of two things. It's a weighted sum of the previous cell state. So this is the previous cell state, right? C t minus 1, and the newest candidate cell states. And the weights of these two terms, they are decided by two gates. So this is where this gated thing comes from. Right? We have this forget gate, F for forget, and you have this input gate, I for input. Right? So, and this operator here, it denotes the element-wise product. So basically, what this says is that this forget gate is going to control the weight of this previous cell state, C t minus 1, every entry of it, because it's a element-wise gate, right? So for every entry, it's going to control every entry of this C t minus 1. Right? So this is the forget gate, and similarly, you have the input gate to control the weight of every entry of this candidate cell states. So the final cell state is computed as the weighted sum of these two things, the weighted sum of the previous cell state and the current candidate cell states. Okay. And after this, we say that, right, before we say that the output state H is actually a subset of the memory state, right? So H is a subset of C. That means to compute H, we will need to take the cell states, right? So this is the cell states, and it's going to go through some nonlinear operation, and then you have this output gate, O for output, okay? O for output, and this output gate is going to control every entry. It's going to be a weight, right? And this weight is going to control every entry of this cell states, right? And you can see that this output gate, to compute this output gate, it's gonna use a sigmoid function. The sigmoid function, what's sigmoid function? The sigmoid function has a range between 0 and 1, right? Between 0 and 1. That means at most you can keep all your cell states, but in the worst case, I'm going to throw away the cell states, right? So because if it's 0, then you're going to completely remove the cell states. If it's 1, then you're going to keep the cell state. So this is why we say that this H is actually a subset of C, because it uses the output gate to control which subset of C is going to be moved into H here. And you can see that you have these three gates, right? You have this forget gate, we have this input gate, and we have this output gate. And all these gates, they are computed in a way that's very similar to how we compute the H in the vanilla RNN. The only difference is that these are the gates, right? The gates controls whether you can go through or not. Then the basic property of a gate is that it's going to be in the range of 0 to 1. And in order to satisfy this property, the natural choice would be to use the sigmoid function. So every gate, they are parameterized by a linear combination of the input, the previous output state, and also the bias, of course, and followed by a nonlinear activation. And this is usually using a sigmoid function because it has an output range of between 0 and 1. Okay. So this is the LSTM. Okay. LSTM first compute the candidate cell states, and then it computes the current final cell states and compute the output states. Right. And in the course of computing all this, you will need to compute 3 gates. So these are the 3 gates: input gate, forget gate, and output gates. Okay. And when you're computing this, you're gonna go through different parameters, right? So all this W, so this W x1 is WS1 means that this weight actually connects the input, which is X, into the input gate, right? So this is why you have this X and I, right? And you have this WHI. That means this weight is actually connecting the output state H, right? This is why you have this H, and connecting the output state to the input gate, and this is why you have the I here, right? So this is just for intuitiveness. Okay? And similarly, you have this WXF, so F for forget, and you have this WHF, right? So all these parameters you have to learn from your data. Okay? All the X, all the W and all the B, you need to learn from the data. Okay? So this is the LSTM, a overview, and in the next few slides we're gonna go through this with some visualization and hope that I can help you understand better. But before I move on, let's see if there's any questions in this computation process of LSTM. Questions? The cell state is visible as well. Cell state is actually not. By other part of the network, what we mean is that what you use to predict Y. When you're predicting Y, you're going to use H to predict Y. So so in here, right? In here, this is going to be H, and you're going to use the H to predict Y1, right? Yeah. Yeah, that's the other part of the network. And also, this is a good question, because sometimes you will need to stack multiple layers of RNN, right? So this is one RNN, and you might want to stack another RNN on top of it. Then in another RNN, an RNN needs to take input X, right? So you're going to treat this H as the X as your next RNN, right? So this is another meaning of other part of the network. Yeah. Cool. Good questions? Any more questions? What's what? Oh, forget gate. What's the forget gate? Forget gate is here, right? The forget gate is used to control how much information you would like to forget about the previous cell states, right? This is the forget gate. So what's the question here? Or is it clear now? It's not. So when you compute the forget gate, so when you're computing this is not forgetting yet. So when computing this FT is the forget gate. The forget gate will control how much you forget and how much you remember. But the forgetting happens here, not here. Okay. So this is just to compute the gate. And this X, so to compute how much you forget and how much you remember, you will need to look at your current input, right? Look at your current input and look at your previous output state, right? And then you can try to decide what part of the cells that you want to forget and what part of the cells that you want to remember, right? So this is for computing the forget gate. And the process of forgetting happens here, not when you are computing the forget gate. Okay. Cool. Good question. And other questions? in practice, these gates seems to automatically learn for themselves to avoid this problem. But your question is a good question, and this is exactly what motivates gated recurrent units to move beyond LSTM. And gated recurrent units, we're going to talk about this maybe 10 slides later or in the next lecture. It's exactly what you said. So it's not going to have two gates. It's going to have one gate, and it's going to be this is the gate on the left, and on the right it's going to be 1 minus that gate. Yeah, that's a good question. Any more questions? Okay, so this is LSTM, and we're going to briefly go through some kind of visualization, and we're going to end this lecture. So this is one of the diagrams to show the process of computing LSTM, the whole process. Okay, so you're gonna. The first step is to compute the three gates, right? The forget gate and the input gate and the output gate, right? And to compute these gates, you would need the previous output state or hidden state as input. You also need a current input, right? So you can see that this is your x and this is your h, right? X, h, right? You're going to need these as input, and you're going to go through different parameters, right? You're going to go through these parameters to compute your input gate, right? You go through a different set of parameters. Basically, it's a small network, right? It's a different small network to compute the forget gate, and going to go through another parameters to compute the output gate, right? So this is the first step: compute the three gates, and then you're going to compute the candidate cell states. To compute the candidate cell states, you also need the current input and the hidden states, right? Current input and hidden state. And you go through some small linear network, right, with these weights and bias to compute the candidate states. So you can see that they all use the same input. Therefore, this structure looks very nice and parallel. After doing this, it's going to get slightly more complicated. You will compute the final cell states as a weighted sum, right, of the previous cell states and the current cell candidate, right? So to compute this, you're going to have two things. Right? You need the previous memory. The previous memory is going to multiply element wisely with the forget gate, right? So this is element-wise product. So this is the first term. The second term is going to take your candidate cell states. So this is your candidate cell states, right? Your candidate cell states and your input gate, and you're going to take the element-wise product, and then you're going to add them up, right? You're going to add them up to get your final cell state in the current time step. And then we're going to compute the subset of the cell state which goes into the final output states. So which is going to be here. So this is the final output state, right? It's going to be a subset of it. To compute the subset, you will need your output gate here, and you will need your current member. So this is your current member, right? CT. So you're gonna go through some hyperbolic tangent, right? And then you're gonna take the element-wise product between the output gate and this one, and you get your finals. Okay, so this is LSTM. I hope it's all clear. And so this LSTM and gated recurrent unit, which we're going to cover in the next lecture. So it's going to be one of the key component in our third homework. So our third homework is not mandatory; it's an optional homework. It will serve as some kind of extra credit if you want to do it. Okay. And also, someone mentioned to me that the deadline of the second homework actually is in the middle of the spring break, so I kind of postponed the deadline to 3 days later. So it's going to be the Monday after the spring break. Okay. And remember to submit it on time. And also, the proposal is due. I think it's due in this week. So remember to submit it too. All right, so have a nice day, and this is it for today's lecture.